Hello, today we're continuing our A-level revision series looking at superconductivity. We'll cover a little more than you need for A-level so that you know what's going on. A substance becomes superconducting when its resistance is 0. And that usually happens at very low temperatures, often as low as of the order of 10 degrees Kelvin, which is minus 263 degrees centigrade. One obvious advantage of superconducting materials is that there is no power loss when electricity travels through them. Power is equal to I squared R. And if R is 0, then the power loss is 0. It also means that when a current starts to flow in a cable that is superconducting, it will flow forever, even if there's no battery or other power source, because there's no resistance, so there's nothing to stop the current. We can explain this by Ohm's law, V equals IR. If R is 0, then V is 0. Even though there's a current, there doesn't have to be a potential difference because the resistance is 0. Superconductivity was discovered by scientists who were measuring the effect of resistance according to temperature. If, for example, you have a battery that is making a lamp, this is a lamp, glow, there will be a current flowing in the circuit. And what they found was that as the temperature went down, so the light glows more brightly, because its resistance decreases. And so for any given voltage of the battery, if the resistance goes down, the current goes up and the light glows more. And the graph of resistance against temperature looked like this. As the temperature was brought down, so the resistance came down. Until you got to a point, but I have to say this point was something like 10 degrees Kelvin, when all of a sudden the resistance falls sharply to 0. Now, to understand why that happens, we first need to understand what is happening when a current usually flows through a wire. A current is, of course, just a collection of electrons travelling in a particular direction, usually towards the positive terminal of the battery or the power source. But electrons are travelling through atoms. If it's a copper wire, atoms of copper. And so they're constantly bumping into atoms, and when they bump into them, they cause those atoms to vibrate. And that transfers some energy from the electron to the atom, and that comes away in the form of heat. And so you lose energy, and that's essentially what resistance is. We saw in an earlier video how copper is able to produce free electrons that are able to travel and conduct electricity. But let's just think about exactly what is happening in the copper wire, and let's look at, say, a very small chunk of that wire just there. We'll magnify it up and we'll ask ourselves what is actually happening inside the wire. Well, here's the wire. And it's made of copper, which means that there will be a lattice of copper atoms. Here they are in the copper wire. But those copper atoms have given off the electrons in their outer shell, and so they will be slightly positively charged because they are electron deficient. There will, of course, be at the end of the wire the huge positive terminal of the battery. And there are also electrons which are negatively charged flowing through the lattice to get to the massive positive charge. Now, what is the perspective of any one electron? Well, for a start, the electron will want to keep away from other electrons because like charges repel, and so electrons won't want to get too close to one another. On the other hand, the electrons might well be attracted to the modest positive charges of the copper atoms, and they'll certainly be attracted to the massive positive charge of the battery. So they will essentially wend their way through this wire by trying to keep away from other electrons, being slightly diverted towards these positive charges en route to the massive positive charge here. But as they travel through the copper lattice, not only will they be attracted to the positive charge, but of course the positive charge will also be attracted to them. And so you will find that the atoms very slightly distort in the direction of the electron. And that distortion creates, for the time being, a larger positive charge in the middle of the copper lattice. And that of course means, if we redraw that here is a positive charge because some of the atoms of the lattice have been drawn together because there are a few electrons about. That means that more electrons will be attracted to that positive charge. And that gives rise to a tension. On the one hand, the electrons want to move towards this positive charge. On the other hand, they want to keep away from one another because they are all negatively charged and like charges repel. And what happens is that there is a quantum mechanical effect whereby electrons form into pairs. And those electron pairs are called Cooper pairs. The trouble is that the energy of bonding of those Cooper pairs is 10 to the minus 3 eV, which is a very small energy. For example, room temperature has an average energy of a 40th of an eV. So at room temperature there's enough energy to break those bonds. How far do you have to go down in temperature in order to keep those bonds together? Well, we've already learned in other videos of a relationship that says that energy is equal to Boltzmann's constant times temperature. And when energy is measured in electron volts, then Boltzmann constant is 10 to the minus 4 eV per degree Kelvin. So if energy is 10 to the minus 3 and K is 10 to the minus 4, what is T? The answer is that T equals 10 degrees Kelvin. So if you can get the temperature down to 10 degrees Kelvin, then the energy of the Cooper pairs will not be split, or rather the energy which is holding the Cooper pairs together will not be overcome. Now, how does it help to have Cooper pairs? Well, an electron, as we've seen from previous videos, is what's called a fermion. Everything in the world is made up of either fermions or bosons. Fermions are essentially the fundamental particles, and bosons are the things that exchange with forces. A typical boson would be a photon, that particle of light. The Pauli exclusion principle applies to fermions but not to bosons. What the Pauli exclusion principle says is that no two electrons, or indeed any fundamental particle, can occupy the same energy state. But if two electrons form together to become a Cooper pair, and that is a boson, then it will not be constrained, and consequently lots of Cooper pairs can all occupy the same energy state. And one of the consequences of this is that these electron pairs, which are bosons rather than fermions, do not suffer any resistance from the lattice structure. They are what are known as a superfluid of Leon Cooper pairs. It was Leon Cooper who first discovered this. These are pairs of electrons that arise because of what are called the exchange of phonons. Phonons are just a collection of excitations of atoms or molecules, but all doing it together, so it's as if all these atoms and molecules are together vibrating in some collective mode. And that's essentially what's called a phonon. And that collective interaction, or that collective excitation, produces the Cooper pairs, which become bosons rather than fermions, are not subject to the Pauli exclusion principle and can pass through the wire unhindered, and that's why you get zero resistance. Now, one of the effects that you might have seen on a YouTube video is levitation. You can find these very easily by looking up superconductivity on YouTube, and what you usually find is that there's a dish with a metal in it, and that is covered by liquid nitrogen. So it's very cold. This is liquid nitrogen, and this is a metal. And then what happens is someone places what actually is a magnet above this solution, and the magnet simply stays there. It doesn't fall, it stays, even though this is not a magnet. Why does that happen? Well, ordinarily if you have, say, a metal, here's a metal, and you have a magnetic field, external magnetic field, then the magnetic field will just go straight through the metal. But if you cool the metal down to below its critical temperature so that it's in the superconducting range, then what happens is that it will exclude the magnetic field. The magnetic field can no longer pass through the metal. And that is called the Meissner effect. How does it do this? Well, what it does is that in the metal, which is now superconducting, it sets up little surface currents, which, because this is a superconductor, can flow as surface currents forever, because there's no resistance. And surface currents, we all know that if you have a current flowing through a wire, that will generate a magnetic field. Well, surface currents will also generate a magnetic field. And if you have a magnet here, it has a magnetic field, and the two fields then interact. And consequently, it's rather like two north poles keeping one another apart. Two poles repel. And the superconductor will always have currents flowing in such a way as to oppose the field that's coming towards it, in order to cause that field line to divert and go away. And consequently, you get two like poles, and that causes repulsion, and that's what keeps this magnet levitated. And there's no magnetic field in the centre of the metal at all.